We're going to look at the immediate value theorem. So this is what the immediate value theorem says. It gives this condition. Suppose a function is continuous on the closed interval a to b, and then let y naught be any number between f of a and f of b, and the theorem then says that there exists a c on the closed interval a to b such that f of c is equal to y naught. So let's draw a diagram here to help us see what's going on. Okay, so there's this interval that the function's continuous on. It's a closed interval a to b, and it's continuous on the closed interval, so it's defined at a and b. And just as an example, let's just say this is f of a, and then we can say that this is f of b. Okay, and these could be anywhere. F of a could be up here, f of b could be down here, and this thing could oscillate up and down, however it is, but I'm going to keep it real simple. To say that it's continuous on f of a to f of b means that I need to be able to draw the graph without picking up my pencil as I go from f of a to f of b. So however I draw it, okay, I can't lift up my pencil to connect these 2 points. That's what it means to be continuous on the closed interval a to b. So what this is saying is that for any number between f of a and f of b, so I don't know, we'll say right here, we'll say that's y naught. For any number in this interval, there's going to be a c down here such that that the function is going to equal y naught at that point. And so you can kind of see why this is true, because two things have to happen, right? Like, in order for it to not be true, I got to connect these 2 points up without lifting up my pencil, but then I couldn't cross this dotted line if the conclusion were not true, and that would be impossible, right? So, for example, let's say I go like this, and then here would be my point. This would be the c, right? And I would get that f of c here would equal y naught. Okay? And so I couldn't, for any value in between f of a and f of b, I couldn't connect these 2 points up with a function so that it didn't equal y naught for some c inside this interval. Okay? So the theorem is very, very intuitive and very obvious. Now, it's not so obvious to prove, and in fact it involves the completeness property of the real numbers. It's kind of a deeper, more abstract proof, but as far as a theorem, it's pretty obvious. One way to think of it is that between a and b, the function is going to take on every value between f of a to f of b, right? Because you got to connect them up with an unbroken line. So every value between f of a to f of b is going to be taken on by the function between a and b. So if you pick one of those values, then there's going to be a c between a and b such that f of c is equal to that value. So that's the intermediate value theorem. This gets used in a lot of other proofs. It's one of the things that you need to prove other things. And it can also be used. This is a very simple example of how it could be used. This doesn't necessarily help you find the root to an equation, but you can use it to show that there is a root to an equation. So here's a polynomial, and it wants me to use the intermediate value theorem to prove that this function has at least one root between x of 1 and x of 2. Okay? So let's look at what's going on here. So let's say this is 1 and this is 2. Okay? And what I'm going to do is I'm going to find out the value of f of 1 and the value of f of 2. Okay? So if I plug in 1 up here, I'm going to get 1 minus 3. That'd be negative 3 plus 2 would be let's see, let me do it again. 1, this would be 1 minus negative 3 would be negative 2, plus 2 would be 0, and this would be negative 1. There we go. That's the number I was looking for. So f of 1 is equal to negative 1. So this polynomial, let's say this is 1, is going to go through this point. So this is the point 1, negative 1. And our polynomial, however it is going through that point. Now, at 2 here, this is going to be 8 minus 6 is 2, plus 4 is 6, minus 1 is 5. So at 2, it's equal to 5. So let's say this is 5 up here, right? So this is the point 2, 5. Okay, so now this is a polynomial, and a polynomial is a continuous function, continuous at every point. So this function, no matter how it goes, has to go from this point to this point. I have to be able to connect these 2 points up without lifting up my pencil. Now the question is there any way for me to do that without crossing the x-axis? So the root of this equation is where this polynomial is equal to 0, and that's going to be where the polynomial crosses the x-axis here. Is there any way then that I could connect this point up with this point without crossing that axis? The answer is no. I'm going to have to cross it. And so that proves that there's a root there. So, and you could write it like this: since y equals 0 is between f of 1 and f of 2, then there exists a c between 1 and 2, or on this interval 1 to 2, such that f of c is equal to 0. And that's going to be a root. And in fact, this thing, I think, is going up here. So I actually have the function here. Here's a graph of it. And so you can see that this function is it's like going up, and it's going down, and then kind of going back up. And then this would be the c here, where you get a root to the equation. Okay, so this is an example then of how the intermediate value theorem could be used to actually prove that there was a root to the equation between 1 and 2. And basically the way that you do that is that you show that one of the endpoints is negative if the other endpoint is positive, and it doesn't matter which one is which, because the polynomial could be going down like this. But if one is negative, one is positive, and the function is continuous between the two, then that means the function is going to have to take on the value of 0 between those two. If it changes signs, it has to pass through 0, and that is a root of the function.